you heard of them? Did you just heard Jin Xiaojing?
I'm so sorry.
What's the answer? Converges or diverge? Who says it converges? Who says it diverges? It converges, right? Why? Because you take the integral from 2 to infinity of 1 over x natural log of x squared, right? And you play exactly the same game. You're going to get u to the minus 2 du natural log of 2 natural log of b, right? You do the same substitution, right? You get negative u to the negative 1 between natural log of 2 and natural log of b. And so you get negative 1 over natural log of b plus 1 over natural log of 2. Right? Sorry, I should put limits here. Right? And so you end up with 1 over the natural log of 2. Right? Okay. So let's explain why this happens. Why does this happen? Why does this work? Okay. Why does this work? So here's the picture. You have this function that is continuous, decreasing, and positive, right? So you have this function, and it's going down like this. This is your function, right? And the thing that we're interested in is the sum. We're interested in the sum of f of k from k equals 1 to infinity. Okay, so we're going to put that into the picture. Here's 1, 2, 3, 4, 5, 6, 7, 8, etc. Okay, so we're gonna draw this sum in the picture. And say, okay, well, if I come up to here, then that's f of 1, right? So this block has area f of 1, right? If I draw a point here, that's f of 2. So this block has area f of 2, right? This block has area f of 3. This block has area f of 4, etc., etc. Okay? So what you see is that the integral from 1 to n of f x dx is smaller than the sum of f of k from k equals 1 to n minus 1. Right? Here, the integral from 1 to 5 is smaller than the sum of f of k from k equals 1 to 4. Right? You see that the integral is smaller than the sum of the blocks. Right? The integral up to this point, 5, is smaller than the sum of these first 4 blocks. Okay? Now you could also do the following. You could also go like this. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. If I come up to f2 and I go to the left, then this area is f of 2. This area is f of 3. This area is f of 4. This area is f of 5. Okay, so in this case, what you say is that the integral from 1 to 5 of f is bigger than or equal to the sum of fk from k equals 2 to 5. Right? So on the other side, what I get is the sum from k equals 2 to n fk. Right? Okay. Now, suppose, so what this basically tells you is that if this guy converges, then the integral converges, right? If this sum converges, then the integral converges. If the integral converges, then the sum converges, right? And that's what we're hoping for, that if the integral converges, then the sum converges. If the sum converges, the integral converges, right? So this observation basically gives that to you. Okay. So you say, well, look, right? Suppose fk is some number L. Suppose fk is some number L, but then the limit as n goes to infinity of the integral exists, right? Because this is a monotonic non-decreasing sequence. Non-decreasing sequence. It's a non-decreasing sequence, right? And so if it's bounded above, then it converges, right? Right. Here in a monotonic sequence, if the right hand reaches a limit L, what we see is that this sequence is bounded, so converges. Okay, and then going the other way, suppose the improper integral exists. Well, in that case, then the sum of f of k from k equals 2 to infinity converges, because it's bounded, right? This guy from 2 to n is bounded, so converges. As n goes to infinity. Okay. So I'm cheating you a little bit, but this is basically the idea, right? This is basically the idea that, look, the partial sum of the series is bigger than the integral from 1 to n. So if this thing converges, then this guy is going to also converge. Okay. Similarly, right? If this integral converges, well, this is bigger than that, and so this is the partial sum sequence will be bounded, and so converges, right? So this all is based on the monotonic sequence theorem, right? So keep in mind the monotonic sequence theorem that says that if monotonic, a sequence converges if and only if it's bounded. I think it's a good time for you to talk to each other. Talk to each other for a minute and see if you can clarify questions or formulate or clarify questions. Yes, one more.
1 over n mod, is that bounded?
I mean, the integral turned out to be divergent, right? So no, it's not bounded, right?
Why is that?
Remember, what we saw was that, right? So I think you're asking about this one over this. You're asking about this one, right? So for this one, you have to consider 1 over x natural log x dx, right?
I mean, it's a function bounded.
The function. Okay. So the function is bounded. The function is bounded, right? But the integral is divergent. Okay, so yeah, don't watch out for this, right? The function is bounded. Certainly, the function is bounded, right? But let me make it more obvious. Look, this thing converges if and only if this thing converges. Okay. Now 1 over x. That is, that's a bounded function, right? From 1 to infinity, 1 over x is a bounded function, right? But the integral is divergent. The integral is infinite. Okay. So don't get mixed up here, right? When we say when we're talking here, we're saying that like the partial integrals are bounded. Okay. That's the partial integral. It's not the function. It's the integral from 1 to n, right? So if we look at, say, 1 over n squared, right? And that's related to this. If we look at this thing, right? So and here you've got 1 over n squared, like this, right? And what we're saying is that the integral from 1 to n is bounded, right? All of these integrals from 1 to n are bounded, right? Right? If you take the integral from 1 to n of 1 over x squared dx, right? You're going to get negative x to negative 1 between 1 and n. That's going to be negative 1 over n plus 1, right? And you see that all those numbers are bounded. Okay, that's what we're talking about, the partial, the partial integrals. Okay. So those are the things that need to be done. Those are the things that are bounded. The partial integrals are bounded, and so the whole integral becomes bounded, right? So yeah, so don't get confused between the function being bounded and the integral being bounded. Those are very different things, right? Here the function is bounded and the integral is bounded. Here, the function is bounded, the integral is not bounded, right? The integral is divergent. It's very different. Other questions? Okay. Let's go back to here. Were people able to figure out? People able to understand what's going on here? Right. The key is this. The key is this. This is the key observation. That, well, look, right, and it's in these pictures, right? If the sequence converges, that forces the integral to converge. If the integral converges, then that forces the sequence to converge, right? Because here we see that the sequence is bigger than the integral, and here we see that the integral is bigger than part of the sequence. The series, I'm sorry. Right? If the series converges, then the integral converges. If the integral converges, then the series converges. Okay, so that's what we're trying to show. I hope you have some sense of this. Maybe I should have done the following test first. So there's something called the basic comparison test. Yeah, actually, maybe doing this one first would have made more sense. So you have A sub n, B sub n. These are non-negative series. That is, A sub n is bigger than or equal to 0, and B sub n is bigger than or equal to 0 for all n. Suppose that A sub n is less than or equal to B sub n for all n past some point. When, if the sum of the bigger guys converges, then the sum of the smaller guys converges. If the sum of the smaller guys diverges, then the sum of the bigger guys diverges. Yeah, actually, I should have introduced this first, because that's basically what we're saying here, right? We've got a bigger, we've got some bigger guys, and we've got the smaller guys, right? Okay. So let me give you an example. Let's see. So if somebody says natural log of k over k cubed from k equals 1 to infinity. Summation of natural log of k over k cubed from k equals 1 to infinity. And you'd say, oh, well, I know that natural log of k is smaller than k. Right? Natural log of k is smaller than k. So I know that natural log of k is small over k cubed is smaller than k over k cubed. Right? And I know, and since summation 1 over k squared converges, we know that summation natural log k over k cubed converges. Right? You find somebody that's bigger, that converges. Right? Find somebody bigger that converges. Right? The bigger guy converges, so the smaller guy converges. Okay. Notice that you could have done something useless if you had said, oh look, this 1 over k squared is smaller than 1 over k, and the 1 over k diverges, right? That's true, but that wouldn't help you at all, right? You would find somebody bigger that diverges, and that doesn't tell you anything about this, right? You need to find somebody bigger that converges, right? If you find somebody bigger that converges, that helps you. That gives you information. If you find somebody smaller that diverges, then that gives you information. But finding somebody bigger that diverges doesn't tell you anything. Finding somebody smaller that converges also doesn't tell you anything, right? So you have to think of what you're trying to. You're trying to get information. So yeah, you have to keep your goal in mind. Okay. Let's see. Okay, another example, or maybe I'll let you try it. 1 over natural log of k, from k equals 2 to infinity. Okay. See if you can find something to compare this to that will give you some information. Okay. Find something to compare with that will yield information. Okay, turn to somebody nearby and say what you're doing. Okay, so what do you compare against? What do you compare against? 1 over k, right? 1 over k. You know that natural log of k is smaller than k. 1 over natural log of k is bigger than 1 over k, right? And you know that summation 1 over k diverges. So you found a smaller series that diverges. So the bigger guy diverges. Okay. Here's another one. Summation 1 over root k plus 1. Okay. Summation 1 over root k plus 1. This one is maybe a little bit harder than the other ones. But try it for 1 minute, and then then I'll show you how to do it. Okay, turn to somebody nearby. Say what you're doing. Okay, would somebody like to say how they do it? First off, is it convergent or divergent? Is it, okay, who says it's convergent? Who says it's divergent? Okay, so yeah, so you look at it and you say, well, this one doesn't really matter, right? In thinking about the convergence, as k becomes really large, this one isn't really going to matter. This is basically going to be 1 over root k, right? And we know that that the power, since the power is less than 1, this is going to be divergent. So this is going to be divergent. So how do you show it's divergent? You want to, by using the comparison test, you want to find something smaller that's also divergent, right? So what do you use that's smaller? 1 over root k? Is that smaller than 1 over root k plus 1? I don't think so, right? Is it? Root k plus 1 is actually bigger than root k. So 1 over root k is bigger than 1 over root k plus 1, right? So you don't want to compare it against this because that's actually something bigger that diverges, right? But you can do something. You can do something very similar. Did anyone figure out some way to do it? Do a comparison. Here's one thing you could do. You could say, well, look, root k plus 1 is smaller than root k plus k, say. Right? So square root of 2 root k. Right? And so 1 over root k plus 1 is bigger than 1 over root 2 root k. Right? And you know that the integral of 1 over root k, 1 over root x diverges. So you could do something like that. Okay, everyone take a break. Take 5 minutes. 5 minutes of break.